So we're going to start off with this fictional story. Carrie is out walking on a country road when a man pulls up and kidnaps her. He shoves her in the trunk and starts heading east along the road. Carrie calmly gathers herself and pays careful attention to the man as he drives along. Every so often, the man checks in with his mother to see if she's okay. Each time he calls his mom, she asks him what his speed is at the time, out of concern he might be speeding. Little does he know he's kidnapped somebody. Luckily, Carrie has her cell phone with her and makes a mental note of the times when he tells his mother the speed. So we have the times and his speed. After the last time, which is a half hour into the trip, the man pulls her out of the car, leaves her on the side of the road, and drives off. Unfortunately, just like the entire trip, she has no phone service. She decides to climb a nearby hill to get to higher ground and hopes her cell phone will work. Luckily, when she reaches the top, she gets phone signal. She immediately calls the police. Unfortunately, they ask her where she is so they can send her a car. She has no clue. She doesn't even know how far they went. But can we figure it out given the information present? So if you want to start, pause the video, take a few moments and see if you can come up with an estimate as to how far she ended up from where she was abducted. So once you have your estimate, there's a way we can calculate the exact distance. So let's think about the process. Here are time and the speed at each point. Now, I know distance equals rate times time. So we can kind of get an idea of this, maybe. There's several different ways we could do it, though. Let's assume first that the speed stays the same as the last speed spoken. So, in other words, this speed was the same, remain constant, and then we drop to this next one, right? And then this one's going to remain constant until we get here. And then this one's going to remain constant until we jump up to there. And then this one is going to remain constant until we get here. So we were at 40, is that miles per hour, for how far did they go there? So the time was 0.10 and then 0.15. So in 0.05 seconds, they were going 40 miles an hour. In this section, it's 0.10 hours at 30 miles. So from here to here is 0.15 at 45 miles an hour. Then from here to here was 0.10 again at 50 miles an hour. So this speed for this long should give us the distance traveled there. So we can use our calculator to add this up. Let me see if I can get this where you can see the calculator too. 0.05 times 40 plus 0.1 times 30 plus 0.15 times 45, 0.1 times 50. So 16.75 miles. Now, we're leaving off some stuff, right? So how fast were they going in the first 10 seconds? We don't know. And we didn't even take into consideration when he slowed down here. So let's assume that the speed instantly increased to the same speed as the next speed spoken. So let's say they were going 40 miles an hour for the first 0.10, and then they were going this speed, and then it jumped up to there until he talked to his mom, right? And then it jumped up to there until he talked to his mom. And then there. This is called a left sum because we're starting at the left, using that as our left marker. And this is considered a right sum because we're using it as a right marker. So for point 10, we're going 40 miles an hour. And then point 05 at 30 miles an hour. And then 0.10 for 45. And then that's 0.15 at 50. Oops, I forgot the plus sign. And then 0.10 at 30 miles an hour. Times 30. That sounds a little bit better. But does the speed instantly jump up? No. So what about if we got halfway? We took an average. So let's assume when he picked her up it was 0, right? And then the next time he talked it was 40. So let's go with an average. What if we say for that time they were going about 20? Well, so that was, he said he was going 40 miles per hour, and then here he's going 30, so a good average should be 35 miles per hour. And then he said he was going 45, so a good average would be 37 and a half. So here we had 45 to 50, so a good average should be 47 and a half miles an hour. From 50 dropped down to 30, so an average for that time span would have been 40. So for the first 0.10, the average was 20 miles per hour. For the next 0.05 hours, the average was 35. For the next 0.10, the average was 37.5. For the next 0.15 hours, the average is 47.5 miles per hour. And then for the last 0.10, the average speed would be 40. So I'm going to add those up. You know, sometimes it's hard to see the screen. 0.1 times 20 plus 0.05 times 35 plus 0.1 times 37.5. 5 times 47.5. So for each of these, remember what we're doing, this is the time spent going approximately that speed. So that'd be the distance they traveled in that time. Time spent, approximate speed. This is giving me 18.625 miles. That's sounding a little bit better. What about if we assume that the speed actually changed slowly from one speed to the next? Because people don't automatically go a certain speed. They gradually change their speeds. So if we did that, we'd end up with something that looked more like this. He started at 0 miles an hour and steadily increased to 40. And then slowly drop down to 30. And notice I'm bringing my lines down so we can create figures. if I look to the side, each of these shapes is actually a trapezoid. Well, the first one's technically a triangle, but they're trapezoidal, right? So the first one would be 1/2 base, be that, which is 40, times the height, which is that distance there. The next one is actually trapezoidal. Trapezoid, it's 1/2 base 1 plus base 2 times the height. Base 1 and base 2 are these two different lengths here. So this one's 40 plus 30 times the height of the trapezoid, which is that difference in time. Then next, 1/2 base 1 plus base 2 times the height of the trapezoid, which is this. Base 1 plus base 2. So 45 and 50. Times 0.15. And then we have plus 1/2, 50, and 30. Times 0.10. Now to save you on that, I went ahead and added it up, and lo and behold, it gave me the same exact thing as the midpoint sum. The reason being, half of 40 is 20. Half of 70 is 35. This is actually taking the average of those two bases. So it technically comes out to be the same thing as if we went with the midpoint. Notice in each case, to find the distance traveled, we really just found the area underneath the function. So clearly finding the area under a speed graph, or the velocity, gives us the distance traveled. So what was the relationship between speed or velocity and distance? Well, velocity was the derivative of distance. It was the rate of change of distance. So there's going to be times where we need to find what is called the antiderivative. What that means is we're going to be finding the function who has a certain derivative. So remember, velocity is the derivative of distance, and we found the distance by finding the area under the curve. So we're finding the distance, which velocity is the derivative of. So when we were given the derivative, which was speed or velocity, and we're trying to find information about the original function, we have a shorthand notification that we'll learn later. But there's 4 strategies to estimate the area of the figure we actually